Hello, everybody. My name is Fabiola Trujano Jimenez, and I will present today my project called Two-Dimensional Ekman-Inertial Instability, which I am working with Dr. Barbara Zemskova and Dr. Nicolas Grisua at the University of Toronto. So here's an outline of my talk. I will give some background information to introduce the Ekman-Inertial instability. Then I will present my setup, the setup I use for my numerical simulations, and the results that I will present today are focused on the pumping or the vertical flow induced by this instability. I will then summarize with conclusions and some future work. So as we know, there are many reasons why the submesoscale is particularly important in the ocean. First, it has an energetic relevance, meaning that it provides a link for dissipation of kinetic energy from large to small scales, as it is shown in the figure on the left here. And since we find very large vertical velocities in the submesoscale, it also has a climatic relevance because these large velocities, vertical velocities, enhance the fluxes of heat, momentum, and gases between the surface and the ocean interior. Therefore, it also has an ecological relevance because these strong vertical flows also transport a lot of nutrients that are essential for primary production, as we can observe in these beautiful submesoscale filaments visualized by the chlorophyll concentration that indicates a phytoplankton bloom. So this is just a satellite image of the Arabian Sea. And one way in which we find these strong vertical velocities in the ocean is in internal waves. As we know, internal waves are characterized by a frequency constrained by the Coriolis frequency and the buoyancy frequency. And there are several generation mechanisms for these waves. For example, the mechanical forcing from tides and surface winds, the interaction with bottom topography, and more recently, some studies have shown that internal waves are also radiated from hydrodynamic instabilities, and they are also generated spontaneously without any direct forcing. So as you can guess from the title of my talk, my research is focused on the third mechanism. And something we have to keep in mind is that the submesoscale is dynamically characterized by a Rossby number and a Richardson number of order 1, meaning that in the first case, the vertical component of the local vorticity is comparable to the Coriolis frequency, and the stabilizing effect of stratification is also comparable to the destabilizing effect of the vertical shear. So two common submesoscale instabilities develop when these two parameters meet certain conditions. For example, when the Rossby number is less than -1, we find inertial instability. And when the Richardson number is less than this ratio here, we will find symmetric instability. And one way to illustrate this is with this plot that is showing the output of a high-resolution model. And we can see here the color bar is showing the Rossby number. And we see a few mesoscale features, such as these mesoscale eddies or the Gulf Stream. But we also see these small scale features which correspond to submesoscale flows. And we notice that the red colors or the positive values are more saturated than the blue colors. And this is because, as I mentioned, when the Rossby number is less than -1, submesoscale flows tend to be unstable and they cannot be maintained for longer in the ocean. So more recently, the Ekman-Inertial instability has been theoretically predicted to develop in submesoscale flows. And two of the questions that I addressing in my research is, what is the dynamical and energetic role of Ekman-Inertial instability in the submesoscale? And what is the interplay between Ekman-Inertial instability and other submesoscale processes? So first, let me explain how Ekman-Inertial instability works. So it takes elements from two well-known processes. On one hand, the Ekman layer, which develops in flows with Rossby number greater than -1. And on the other hand, inertial instability, which develops in, as I mentioned, flows with Rossby number less than -1. Ekman-Inertial instability also occurs in flows with Rossby number less than -1, but it requires a sudden change in the surface wind stress to develop. So this is what actually triggers instability. And this perturbation at the surface is propagated downward via viscous fluxes. But one of the most interesting features of this instability is that initially it shows a superinertial growth rate that eventually tends to the inertial value as the instability develops. So let me illustrate what I mentioned, what I mean by this. Here I am showing a time series of the ratio between the growth rate of Ekman-Inertial instability and inertial instability. The different curves correspond to different depths. And if we take a look at the white curve, which corresponds to the surface, we can see that the Ekman-Inertial instability growth rate starts at a very large value, and it quickly decays. Here we have 1, so this indicates when the two growth rates are the same. Ekman-Inertial instability decays very quickly, so it reaches a minimum at a value that is actually lower than the inertial value, but then it tends to the inertial growth rate, but at a much slower pace. So this is what I mean by superinertial growth rate, just a significantly larger growth rate compared to the inertial growth rate. And what I am showing here is this was computed for the solution in 1 dimension. So the current description of Ekman-Inertial instability is 1-dimensional. It has an analytical solution, but one of the problems with this is that we need to assume that the Rossby number is constant. And in reality, the Rossby number will vary in space, which eventually will lead to the mix of stable and unstable flow, and will prevent the instability from growing any further. So to account for this effect, my goal is to extend this current description in 1 dimension to 2 dimensions. And for doing so, I am using the following numerical setup. I start my simulations prescribing an exponential velocity field in the y direction. So in this sketch, I show the top view of my initial current. I assume this current is initially in just traffic balance. And I decided to non-dimensionalize my variables using these characteristic length scales, meaning in the horizontal, the half width of the current, and the vertical, the depth of my domain. And for the time, I use the Coriolis parameter, or 1/f. So by doing this non-dimensionalization, I get 3 additional non-dimensional parameters. One is the aspect ratio and 2 Ekman numbers in the horizontal and vertical directions. And I say additional parameters because I already have the Rossby number. So in this case, the equations of motion take this form. These are the Boussinesq equations for an incompressible homogeneous flow that I will close using boundary conditions in the vertical. I have free slit and a rigid lit boundary condition, and I have periodic boundary conditions in the horizontal. I solved these equations using the computational framework Daedalus. And I use the setup that I just showed you to investigate 2 submesoscale instabilities, inertial and Ekman-Inertial instability. In the first case, there is no need of applying any wind stress. So the surface boundary condition for V is set to 0. While in the Ekman-Inertial instability case, this stress that I am applying is proportional to alpha, the aspect ratio. So now I will show you the results of the vertical flow induced in these 2 cases. This is a base case in which the aspect ratio I am using alpha equals 1. And for this case, my Ekman horizontal and vertical Ekman numbers are the same. So if we start the videos, we can observe that in the Ekman-Inertial instability case, the vertical flow is induced much earlier than in the inertial instability case. And we also observe the difference that in Ekman-Inertial instability, it starts primarily from the surface, whereas in inertial instability, since we don't have this wind stress at the surface, and what we are observing is the growth of perturbations within the volume, within the interior of the flow. And something common in the 2 cases is that we observe this, what seems like radiation of internal waves. So to observe, to illustrate this, I am showing Hofmüller plots of the vertical flow. Here I have the across current direction, and in the y-axis I have time in inertial periods. So these plots are taken at half depth of my domain. And as I mentioned, we see this clear difference in the time it takes to for Ekman-Inertial instability to develop compared to inertial instability. And we also observed how the strongest vertical flow is induced primarily within the current. Here, my current is will be pointing out of the screen. And even though we find this stronger pumping in the interior of the current, we also observe wave signature that is being radiated away from the current, like we observe in the animations. So I wanted to know how this vertical flow will change if I change, for example, my aspect ratio. So in this slide, I will show you the results of an experiment with aspect ratio equals 2. So this will be a narrow current compared to the first one. And if we play the videos, again, on the top row, we have inertial instability and Ekman-Inertial instability on the bottom. Again, these two animations start much earlier, but interestingly, inertial instability also takes more time for the narrow current to develop. And something we kind of we also observed here is that the waves that are being radiated in these cases, at least for the narrow current, seem to have a lower frequency compared to the first case, which is being illustrated here. The first thing to note is that the vertical flow is now significantly weaker than in the original case. And as I mentioned, the waves that are being radiated seem to have a lower frequency compared to the base case. However, we still have this clear wave signature that is of the waves that are being radiated again away from our original current. So in contrast, we have an experiment of a wide current with an aspect ratio of 0.5. Again, on the top, we have inertial instability and Ekman-Inertial instability on the bottom. In this case, the vertical flow seems to be much stronger. And the waves that are being radiated are now of a higher frequency. We also observed that the two inertial instability cases are closer in time for the time it takes to be fully developed. These are the Hofmüller plots for these cases. So as I mentioned, this is a much stronger vertical flow that also has this clear wave pattern. However, we also observe that now within the current, we seem to have lower frequency waves, whereas the waves that are being radiated away are higher frequency. Finally, I'm showing the time series of the vertical flow in these three cases. Here is the base case, and we see how this is the main averaged vertical velocity. And we see the main thing I want to that we notice here is this tight trade-off between these two instabilities, in which for the narrow currents, Ekman-Inertial instability seems to have a greater average vertical velocity. In the original case, we have a more similar curves, and for the wide current, we see that inertial instability seems to have a stronger vertical flow. So to summarize, I will leave you with these 3 bullet points. And just as a final comment, right now I am working on exploring the dependence of this pumping on other non-dimensional parameters, such as the vertical Ekman number and Rossby number. And one question that immediately arises when I see these results is, how is energy exchanged between the main current and these internal waves? So my goal is to quantify these energy exchanges, and to do so, first I need to filter the internal wave field from the main flow, and I am using 2 approaches. One is Eulerian and the other is Lagrangian. For the Lagrangian version, I am using grid-based Lagrangian averaging, which was developed by our colleagues from the University of Edinburgh, and I think Hussein will tell us a little more about this in the afternoon session. So with that, I thank you for listening, and I will be happy to take questions.